Swayam Prabha. Digital India. Educated India.
So let's do a small lemma here. So what I want to prove is the following. I want to prove is faces of polytope P is also a polytope which is a convex hull of some. So, let P be is a convex hull of this set, okay, convex hull. So let me write it as this. So, let P be, so let me do it, write it separately. So, faces of P, which is, let us say, write it as convex hull of a finite set A, is also a polytope, and it will be a convex hull of some subset of A. Is this true for simplices? Yes, no? Definitionally, the way we define faces for simplices, this is true. And if we can show that basically faces, this definition of faces and the more combinatorial definition of faces in the simplices are equivalent for geometric simplices, then we are done. But for simplices, we have already proved this, by the way. So, for polytopes, we have to prove it now, right? So, how do we do it? So, you can prove it by this following method. So, see, let us say F is a face of P, okay, the polytope. That means there exists a supporting hyperplane such that F intersection P is equal to F. Okay. Assume that P is contained, P is a subset of H union H plus. Yeah, positive side P is contained. Without loss of generality, I can assume this, right? I can flip the equation and make it if it is on the negative side. Good. So, my claim will be F is nothing but convex hull of H intersection A. To prove. I want to show this. If I have shown this, are we done? We are done, right? I mean, this is something stronger, what I am saying here, even, right? If I can show this, I am done. So, one way is, do we have to show this convex hull of H intersection A is subset of F? Do I have to prove this? Does this need a proof? See, yeah, H intersection A is contained in F, right? F itself is a convex set because F is equal to a convex set intersecting with another convex set, a hyperplane. And this is the smallest convex set that contains H intersection A. So, this part is done. The only thing I have to prove is this. This needs a proof. Right? Okay, so let take a point X belonging to this. Okay. So, let the set A be P1 to Pn. Okay, good. So, I can write X as summation convex combination of with lambda I is greater than equal to 0, summation lambda I is equal to 1. see this x lies on H. No, it's nothing to. So let me take other direction. I should take x in F. Okay. So this x lies on H, right? Because F is equal to P intersection H, right? I have to show this lies on x lies in convex. So H of x is basically 0, right? X is a convex combination of PI's. So H of xi is nothing but summation, I can push H inside. So this is something you have to verify yourself, but believe me, this is true, and this is just one line. You don't have to check, you can just like from definition it follows. Okay, good. See, if there is some, so now if all the lambda i's for which Pi is not in H intersection A is 0, then the point x has to lie in convex hull of H intersection A. So what am I claiming? Let's go to, so let me go to page 1. See, I am writing x is equal to summation lambda I Pi I equal to 1 to n. So let us break it further. Okay. Summation Pi belonging to H intersection A lambda I Pi plus summation, so this let us call this A hat, A minus A hat Pi lambda I Pi, right? Just broke the summation into two parts. Okay. If all the lambda i's here are 0, I will be done, right? Yes or no? Yes. Observe that if Pi belongs to A minus A hat, then H of Pi is greater than 0, because if H of Pi is equal to 0, that Pi should have been in this set, H intersection A. And for this Pi belonging to H intersection A, then H of Pi is equal to 0. See, when I take H inside, this goes to 0, right, because each H of Pi will be 0. I know H of Pi is where Pi belongs to A minus A hat is not equal to 0, is greater than 0. Okay. If the lambda i's, if even the one lambda I was not equal to 0, then Hx wouldn't have been equal to 0, because Hx is equal to 0. Because x lies in F, then all the lambda i's has to be 0 for all Pi belonging to A minus A hat. So what does that mean? In the representation of x, I can forget this term completely. It is just some convex combination of this, but that means x is in the convex hull of H intersection A. So this is the proof. Why the last term is? Oh yeah. So so the thing is, what did we do? So let me just remove this. So this is where this thing is nicer than the board. It will be difficult to remove these lines if I am doing it on whiteboard. So see, I know Hx is equal to 0 because x belongs to F, right? And F is equal to P intersection the hyperplane H. Good. And I also know Hx, so I also know this formula that we have written, right? This one. this formula, that Hx is equal to summation I from 1 to n lambda I h of pi. So, this summation itself, okay, I can write it as this term is equal to this term. Good. All of this is 0 because h of pi is equal to 0. All of this h of pi is greater than 0. If at least one lambda I was greater than 0, then h of x cannot be equal to 0. I would have got a positive value from here. That means all the lambda i's are equal to 0. That means that you can write it as a convex combination of points from H intersection A. So, this is nice, right? I mean, this kind of says that the analogy is almost tight in terms of geometric simplices and polytopes. Obviously, polytopes are generalization of geometric simplices, right? But in terms of the convex hull, how it behaves as a face, they behave similarly, right? Good. So now you can define faces, dimension of the faces of the polytopes also, right? So what will be a 0 dimensional face? It will be a point. Segment will be 1 dimension. It does not have to be segment, it can be like an open, like something like this also is possible, or a complete line also, that is also 1 dimensional face. Okay. So, if the polytope looks like this, let us say, so it is like two intersection of two half spaces where it is open in this direction, both of them, plus side, right. It will be like everything that is contained in this supported on this line and contained in this cone, right, all of the points. Its 1 dimensional face is the whole of this line, right. Faces of the geometric simplices were bounded, right, segments, points, triangles, things like this. Here faces can be like infinite objects also, but that is perfectly fine. Okay. Then you go to planes, not planes, but like 2-dimensional faces, like, okay. And the dimension you define in the same way, right. Dimension is, since the face itself is a polytope, the dimension of the face will be the dimension of that polytope. Okay. So, okay, I made a mistake here. This is for polyhedron, but anyway, so the thing that we are considering is convex hull. So, it will always be bounded. So, you do not have infinite thing. It will come for in terms of polyhedron, but I just messed up. Okay. So, here for convex hull it will be bounded always. Okay. But it may not be a nice face. It does not have to be always a triangle, a 2-dimensional face. It can be like a square. Okay. But let us say, so basically what I said, a convex hull, a polytope will be a convex hull of a finite set of points, right. Good. So, let us assume that the set A is in general position. So, it is a point set in RD, it is in general position. So, no subset of points less than equal to D plus 1 is affinely dependent, all are independent. Okay. So, what will be the faces of this polytope? So, this point set A is in general position. What kind of faces will we see of A? Can there be a square? Let us say D is 10, let us say R 10. Can one face be a square? No, right, because these 4 points are not in general position, right. in R10. So, any subset of size less than equal to 11 should be in general position, right. If A is in general position, okay, this cannot happen. So, a 2-dimensional face has to be a triangle. A 1-dimensional face has to be an edge. 3-dimensional face has to be a tetrad. Like this. Okay. So, any subset of size less than equal to d plus 1, okay, will be affinely independent. That's it. But if that's it. So, if this triangle, let us say this square was present, these 4 points in R10, okay, they are affinely dependent, right, in R10. What about this? What about this? Let us say you have a this square in R3, then is it okay? Still it is not okay, right? Any 4 point should be affinely independent. Even in R3 this is affinely dependent, okay. So, even in R3 this will not happen, but this will be a valid, these 4 points will be a valid general position point in R2. But the faces then will not be this this square, the faces will be these segments, right, these vertices, right, because you have to intersect it with, in R2 you have to intersect this object, the supporting hyperplanes are lines, right. A line can support a vertex, a line can support this edge. Okay. So, this is as a general position point, these 4 points are okay in R2, but anything above that it will not work. But the only thing you have to remember is, if A is in general position, the faces of the convex hull of A will be simplices basically. These are what are called simplicial polytopes. So, I will be mentioning some results which we will not be proved, these are not hard to prove. It is the same way we prove the previous one, you prove these things also, but okay. We have to finish it, finish the course. Okay. So, the thing is, what you can prove is, any polytope P is a convex hull of its vertices. See, all the points of the set A may not be a vertex, right. Let us say the 4 points are like, 5 points are like this in R2. Okay. The convex hull is this square. The center, this point, the point here, this is not a vertex. The vertex are only these things. Okay. So, what I am saying is slightly stronger than just saying convex hull of all of the set A. What I am saying, it should be convex hull of the vertices. Okay, good. Second thing that we want to use is, any polytope can be represented by intersection of finite number of half planes. So, what is a half plane? So, you have this H, you have this H plus or H minus, a half plane will be like H union H plus or H union H minus. Okay. So, sometimes I denote it by this H union H plus, I will write a H greater than equal to 0, this I will write H less than equal to 0. So, what do I mean by that? So, if this is a polytope, then you can write a polytope like union intersection of I equal to some 1 to T H I greater than equal to 0. Okay. All of this needs a proof, but they are not hard to prove also. But okay. Okay, so let us see here. So, now we need a similar object which is called polyhedron. Okay. So, how was polytope defined? Polytope was convex hull of a finite set of points. A polyhedron is kind of like a dual to it. How we define it? It is a intersection of finite number of half planes. So, basically a polyhedron P will be something like intersection of I equal to some 1 to n h I greater than equal to 0 for some h i's. This is a polyhedron. Something you can again show is a bounded polyhedron is basically a polytope. So, for a polyhedron also you can define faces the way we define faces for polytopes, the same way you define faces for polyhedron. The mistake that I made with the polytope thing is polytope has always have the faces will be bounded objects, triangles, rectangles in 2D or something like this, right. But a polyhedron faces can be infinite. Okay, exactly the example that I was saying, writing like something like a half plane that goes in this direction, intersection with another half plane that goes in this direction. So, it will be like this cone kind of a structure, and the hinge, this line, supporting line is a face. Okay. Pardon? See, any faces of the polytope will be convex hull of some set of points, finite set of points only, right. Then I mean, when I was defining it, I made a mistake. It was my mistake. I confused you guys. Anyway. Is okay why it will be finite, but here it does not have to be finite, right? Yeah. Polyhedron. Good. So, let me. I want to state one more result that we will be using tomorrow. So, let me see. Yeah, so let me define what is general position for hyperplanes. So, the way we have general positions for points in RD, you can have a definition of general position for a family of hyperplanes also. Okay. So, let us say you have a family H of hyperplanes H1 to Hn. Okay. They will be in general position if intersection of k of them. So, like take k of them H1 Hk, where k is less than equal to d, intersection of this Hi's I equal to 1 to k, this affine space will have dimension d minus k. And if you take a set of size, if you take hyperplanes of size d plus 1. So, if you take now Hk rather than Hk, if you take d plus 1, this intersection will be equal to empty. This is how you define general position. Okay, you do not have to like this is a definition. Okay. So, this is a notion of what is called simple polyhedron. What are simple polyhedrons? So, see, a polyhedron will be represented as I said intersection of half spaces, right. If the corresponding hyperplanes Hi are in general position, this polyhedron is a simple polyhedron. Okay. So, let me just mention one result incorrectly, but vaguely I will, I mean I will not go into that detail. I will try to sketch out a proof of some duality result between Voronoi and Delaunay and lifting and all this, but I will need this one small result tomorrow, okay, for simple polyhedron. Okay. So, let us say P again, P is equal to, this is almost correct, okay, something like this. Okay. Suppose I say like I is some, let I be a subset of this 1 to n, and I define this f of I, which is equal to intersection of h i's. So, h I is corresponding hyperplane of these half spaces, I belonging to this. It's okay. So, if f I intersection P is not equal to empty, then f I intersection P is a face of P. Okay. Here I am working with simple polytopes, by the way. Okay. So, P is a simple polyhedron, simple polyhedron. Okay. And the second thing is, what will be the dimension of this object? Dimension of, so let us say P is a simple polyhedron. Okay. We get by intersecting it with these half spaces h I greater than equal to 0. H I is the corresponding hyperplane and h I greater than equal to 0 is a plus side, and any polyhedron you can write it like this. You orient the plane properly and you will get it. Okay. Now, you select an index in subset of index subset from 1 to n, I, capital I. And what you have this, you define as f I, which is the intersection of I intersecting all the hyperplanes whose indices are in capital I. This is your f I. Let us say f I intersection P is non-empty. Suppose f I intersection P is non-empty, then f I intersection P is a face of your polyhedron. Okay? And dimension of this object is d minus size of I. Actually, I have written the whole thing. I thought, okay. This is something we will be using it tomorrow. Okay. So, and even more, any face of P can be represented like this, can be obtained like this, obtained by some index set, some set I subset of 1 to n. So, I will try to explain this and then I will end. So, what are we trying to say? So, I am saying, okay, so your polyhedron your polyhedron is basically intersection of these half planes, h I greater than equal to 0. Okay, good. Now, I said, okay, select some set of index set I from this 1 to n numbers, and let us say that intersection of these h i's, where I belongs to capital I, intersection with the polytope is non-empty. That can happen, right? So, like let us say it is of so the half planes were this, and this, and I have got this polytope, right? This whole thing. Okay. The directions of were like this, interior. Okay. This is one H1, this is one H2, H2, H1. H1 intersection P, H2 intersection H1 intersection H2 intersection P is this point. Okay. By the way, up to this point of the theorem, actually I do not need the definition of simple polytopes, okay? Not this one, sorry, up to this. Being a face, this till this you do not need any simplicity, okay? Now, if you are interested in what will be the dimension of the face, can we estimate it looking at the size of I? There you need simplicity, this thing, okay? Again from this point to this point, you do not need any simplicity assumption. Any face, take any face of the polytope, even this face let us say, then you should have taken just H 2 and you would have been done, right. H 2 intersection P would have been this face. This face will be just H 2 intersection P. Right. The only place I need this simplicity assumption is here. Okay. I am, see, this needs a proof, I will not prove it, like, okay, this is not a course on convex polytopes or polyhedron. I will use it to make connections between Vorona and Delaunay tomorrow. Okay. But the main idea is, how do I get the faces of a polyhedron? So, to get the faces of the polyhedron, you just have to find the hyperplanes which supports the half spaces, find some subset of hyperplanes, intersect these hyperplanes with themselves and with the polytope. If it is non-empty, then it is a face. If you have a face of the of a polyhedron, then that also can be represented as an intersection of some hyperplanes and the polytope. That is it. And this see, for the polytope case, the hyperplanes or the supporting hyperplanes that we are building, they are not coming from the points, right? Not exactly coming from the points. I mean, to some extent they are coming from the points also, but here you just look at those, find some subset of HIs, it will give you, and if they intersect, if the hyperplanes intersect and that intersection with the polyhedron is non-empty, it will give you a face. And any face can be, you can generate any face by this method also. That is the result. How do we do it for polytopes? You look at, basically you look at convex, you look at subset of the points, and some of them will, some subset will give, so like the any face will be generated by the convex hull of the points. That does not mean if I take any arbitrary subset of A, it will give me a face, right. Even for convex polytopes, let us say, so let us say the points were like this. So, if I take the convex hull, it will be like the whole of the interior, whole of this, right. But if I have taken these two as a subset and look at that convex hull of these two, this segment is not part of the face, it is one direction only. What I am saying is, if it is a face, then there is a subset of A whose convex hull is the face. Okay. Similarly here, if your polyhedron is defined by some intersection of half planes, okay. If you take a face, so what will be this polyhedron? This will be this blue object, right. So, I am drawing it like this blue object and its interior. So, how I generate the faces? You can generate the face by taking some collection of hyperplanes that are supporting the half spaces and intersected with these hyperplanes with the polyhedron. See, that does not mean if I take arbitrary any two hyperplanes that are supporting some half spaces used for defining this polytope, polyhedron, that I am intersected with P, I will get a face. See, this object, this line and this line, they intersect at this point. And what is this? You can intersect it with the polytope, I get nothing. They are not even intersecting the polytope. Similarly, like this, this segment. Just taking any arbitrary won't work, but any face there will be some corresponding hyperplanes you can take and you get it. Only for the simple polytope property I need is because I want to know the dimension of the face. I can get it by d minus I. If I know the size of I know the dimension of the face. For that I need simplicity, otherwise the rest of the part does not need simplicity. This needs a proof, it is not right. The other one also needed a proof, right. It was not obvious, but the proof is exactly similar, just in the dual setting it works. There it was points, you will work it for hyperplanes. So, I end here.